afternoon, everyone. My name is Thiago Lima Silva. I'm, I think it's called BRU21 graduate. So I was a postdoc. I started in 2018, and then I moved to Sintef last year. And this work that I'm going to present today was a part of the postdoc. And I did this work in collaboration with Alexei Pavlov. And the title is Non-Disturbing Well Testing for Data-Driven Production Optimization. So I basically split the presentation in three parts. We start with a contextualization, trying to define what is the problem that was addressed. Then we go into the proposed solution, how this compares to the current state of the art. And then I present some conclusions, mainly how these can be taken into implementation and what is the way forward for this work. So before, for the contextualization, we are talking about production, daily, weekly. So in this work, we're mostly focused on the short term, not really looking to the reservoir dynamics. And here is the production system. Let me see if this works. Yes. So I bring here like an illustration. So you can see the reservoir here, and the wells are then producing from the reservoirs to the manifolds, the collectors, which lie in the seabed. And then the production is directed to the platforms and to the pipelines, and then they flow up to the risers. And there in the platform, then there is the processing facilities, and like where the production is split in gas, oil, water, also for treatment, and so on. So this is more or less the production system. And what we do, we basically, if you look at the schematic here, try to represent how this looks like, and what we did, what sort of model we used to represent this. We are basically looking to the network. We are assuming that there is like a relationship between like a productivity, using IPRs to represent how the wells produce and so on. And then all the network and all flows and etc. is represented by a bunch of pipelines and connections, like valves and etc. Right? And the overall goal is to maximize the oil production here daily, and we are representing that with Y. And of course, there are you need to take care of constraints in the processing facilities. For example, there is a water handling capacity, liquid handling capacity, and other constraints, right? And that's more or less the scenario. In many situations, in many systems, what is done is that you extract a portion of the gas that you produce, and then you re-inject this gas into the wells. And this process is called gas lift. It's an artificial lift mechanism to boost the production, or to add, in some cases, even to enable the production. And then you basically have a compressor, and then you have UT with the total gas, and you need to split the gas basically into the wells. And this, if we look now into the problem formulation, what we want to achieve is basically how can we maximize the total oil production, given that you can, for example, steer the gas lift rates, how much to allocate of gas for each well. And of course, you need to respect the system constraints. For example, the water production that I just mentioned before, right? So this is a setup, and how to achieve that is basically can be put in the framework of optimization, right? So you can frame it as an optimization problem. So you basically have the objective to maximize Y of T, the total oil production. Then we have some limitations on the compressor. So in this case, we are have a maximum capacity of the compressor. We also have the water handling capacity, the total water that can be handled at the platform. And at the end, we have also some limits for each individual well. You cannot inject more or less. There is a region that you should lie, because if you inject less, then you can produce sand, for example. Or if you inject too much, you can wear the equipment, for example. So then there are limitations, physical limitations, right? And then before we go into the proposed method, what is the current state of the art? So what you can do is basically, given the whole scenario, you have models to represent all of that, and you can do what-if analysis. And this is really typical. You consider certain scenarios and you test with your models and see what's the outcome, right? And then you can make use of first principle models. You can also use data, but in a sense, it's all about trying and seeing how a scenario would, what would be the outcome of a scenario, for example. And then you can also use optimization, but typically it's really hard to couple that with real-time data. And there are some spin-offs working on that, as we saw before. But this is not yet, I can't say that's standard technology being used, right? And the main challenges that are here in these practices are basically, well, modeling errors. So you can build models, but it's really hard to maintain these models and to be sure that the accuracy of these models are good enough. So there are several, it quite often happens that you find a good solution, but the operation condition change, and then whatever you found before doesn't make sense anymore because you have a well that is clogged or whatever. So you need to take into account these changes in operating settings. And also, as I said before, maintenance of model and data, right? How to make sure that you have always up-to-date like models and yeah. So these are the challenges, I would say. And now we go into the proposed solution in this work. And it's basically, well, we basically thought that we can use optimization, but we can try to avoid all the problems and issues that we presented before. So instead of using a model, right, to represent how the system behaves, we decided actually to do something else. That is like, okay, let's try to use, you know, small excitations. And here I'm just showing some sinusoidal like signals. And you can see that you have some degrees of freedom. You can choose, for example, how these, suppose you have one for each well, right? So depending on how you introduce the excitations, they can be coordinated in such a way that the total disturbance is not, it can be zero or near zero, right? And the whole point is that by doing that, and adding some small excitations to well inputs, and then applying that to the production system, and when you measure, like you have the real-time measurements in the system, then you have some field data that can be fed into an automatic optimizer. I'm not going to go into details here, but this optimizer can basically do adaptations in two ways. One is adapting the excitations themselves, and also the well inputs, right? And this whole thing doesn't depend on a model. So you are actually exciting the system, measuring, and moving, right? So that's the whole concept. And if you come back to the current practice, as I mentioned before, well, we argue that the models are inaccurate. It's hard to maintain everything up to date. And if you start doing more testing to get more data, then it's quite costly. You need to stop some wells and so on. And this is very challenging. So with the proposed solution, we basically argue that you don't need to stop your production system. You can do excitations like continuously. And basically, based on real-time data, you can do the optimization continuously without the need to stop. And the whole thing is that these excitations, they can cause some disturbance to the system. And what we did in this work is basically we found a way to coordinate this automatically, such that we don't have any big disturbance, right? And yeah, so if you come back here, the main thing is that we cannot have big variations here, especially for the compressor. So if you have large variations in the input of the compressor, that can be a big problem for the platform. So we are trying to cancel out the total variations, right? And then if you go back now to the proposed solution, then here I bring a plot for that same system I presented before. And I'm showing here like the total water produced, and we have a limit here. And you see in this yellowish line is the standard solution without the coordination of these excitations. And you see that you have these very large variations, right? Because you're not coordinating these excitations. And with the proposed method, you see the black line, and we are able to actually operate quite near the constraint without any violation, right? And that's one advantage, because if you plot then now the total oil production corresponding to this same situation, you see that, well, a way to handle these variations is to decrease the production such that you have a margin, right? But if you do that, then that yields some economic loss because you're not operating near the optimum, right? You're decreasing the productivity such that you're, yeah, on a safe place. But we argue that with this methodology you don't need to do that because you are kind of canceling these excitations. And how that was done, as I said before, you can see the signals for all the systems, and they are quite different. You can see the amplitudes, for example, here and here, And also the phases, they are changing dynamically over time. Okay, that was the methodology that we used. And if you plot now the total disturbance to the system, then in blue here is the total variations, like with standard method without any coordination. And yeah, this black and yeah, red line is basically what we achieved with this methodology. One is the estimated, like what we estimated in the methodology. The other, in the black one, in the red one, is the actual measure data that we got. And that's how the phase and amplitudes of the sinusoidal signals look like. So there are some smooth and nice way of adapting that continuously, right? Yeah, so that was the work, and if I can present some conclusions about what was done. So basically, yeah, I mean, we developed this methodology that can be applied. It was applied for a gas lift allocation problem. And it's basically what we call automatic well testing, because while you're doing these excitations to the system, you're on the same time testing, right? You're tracking changes in operating settings. And so you don't need to pay for additional tests, like to stop in the plant and so on. And this coordination might then avoid economic losses because of these safety margins, and equipment wear, as I mentioned before, like the input in the compressor, for example. You cannot have these large variations happening. And also, yeah, it allows you to operate very near to the constraints without being concerned in having violations and so on. So that's a result. During the postdoc and in the work, we had published some works with the methodology if you're curious about. The first was in ECC, the European Control Conference, in 2020. And that was more or less the beginning, right? Then we extended this for the constrained and more general case. And this was published in the conference, in the IFAC World Congress. And I think this one is more mature. If you want to go in one, you go to the second. And then we are continuing the work. I moved to SINTEF, but we still have this collaboration ongoing with Alexei here at NTNU and some other colleagues at SINTEF Digital. And then we published a third paper, which was, this first one was led by this colleague from the cybernetics, graduated from cybernetics, Mark Haring, who is in SINTEF Digital, and we published this in the journal. And the main advantage of this one is more computationally efficient. And we are like working in the fourth one. There's another journal one that's more, it's more geometric. We found another solution that is better than the previous one. So it's, that's more or less the academic results. And then how I envision that being implemented, like this was not implemented in practice, like this is still simulation-based, right, results. So, I mean, we need to have some the possibility to automatically adjust the well controls, and that has to do with the actuators in the system. So if it's possible to change continuously the choke openings or gas lift rates, that would be possible to implement, right? So that's a requirement in a sense. And also we need to be able to have real-time measurements to be able to then estimate how the system looks like and how to do the projections. And of course we need to do some another project to enable like bringing this concept and all the results that we got in simulation towards more like mature technology, right? So I think only with a project we can do that. And way forward, we have this project ongoing, like in collaboration between NTNU and SINTEF, and that could be a way to continue the work in a sense. But and there are other projects that are relevant and maybe connected to this that could, in a sense, we could consider extensions to the project. But but with that, I would like to finish and thank you all for the attention. And I'll be happy to take questions if I have time. But if not, you can provide some feedback using the QR code. But thank you.